Hello and welcome to the next video. In this video we will discuss semiconductors. We know that there are some materials which are very good conductors of electricity, and there are materials which do not conduct electricity at all, and they are known as insulators. And there are some materials which lie in between the conductors and the insulators. They are not as good conductor as metals like conductors, but they are not very bad conductors like insulators either. They lie somewhere between the conductors and insulators. When we apply a potential difference across them, they do not carry as much current like the conductors carry, but they nevertheless carry some amount of current, and hence they are known as semiconductors. Now, why do some materials behave like conductors, some as some behave like insulators, while others behave like semiconductors? The answer which we know till now is that conductors carry free electrons, and insulators don't have free electrons. That's why conductors are good conductors and insulators are bad conductors. But what about semiconductors then? Because either they have free electron or they do not have free electron. So there are only two states, having free electrons and other not having free electrons. Then why there is a middle state called semiconductors? So now that was a bit of crude introduction to the topic, but that basically lays out what we will discuss in the coming few minutes, which is the concept of energy bands. And the concept of energy bands is basically the correct or more detailed physical view of why some materials are conductors while some materials are insulators and others are semiconductors. So let us study the concept of what are energy bands. So let us take for an example of sodium. So here I have basically given the levels of orbitals. This is the 1s level, this is the 2s level, this is the 3s level, 2p level, and this is the 3s level. So now let us fill the electrons of sodium, and we know that a sodium has 11 electrons, and we'll fill up. I will not go into the details of how much excuse me, how many electrons are there, why there are 2 electrons in 1s and 2 electrons in 2s and 6 electrons in p. I will not go over the detail. Those are the concepts for the modern physics. But Pauli's exclusion principle, if I distribute these 11 electrons as per Pauli's exclusion principle, the 1s can carry a maximum of 2 electrons. So the first 2 electrons will go to the lowest level. So 2 electrons will go here, and this will be completely filled. Similarly, 2 electrons will go into the 2s level, and this will also get completely filled. P level, 2p level can accommodate up to 6 electrons. So 6 electrons will go in this level, and again it will be completely filled. But what about now? We have one more electron left for the sodium atom to distribute, and this will be filled. 3s again can contain a maximum of 2 electrons, but only 1 electron is left. So this will be half filled by 1 electron. and I have more space for the I can accommodate one more electron. So this is the basic distribution of electrons in one sodium atom. Now what happens if I have two sodium atoms, or I have a metal which has many sodium atoms, metal piece. So when I bring two sodium atoms close to each other, as suppose two sodium atoms are very far away from each other. This is the nucleus, this is the 1s, this is the 2s, this is the 2p, and this is the 3s. Similarly, there is another sodium atom here, and these are the orbitals. So the outermost is the 3s. Now, as if they are very far away from each other, we can assume that these orbitals are not or energy levels. Orbitals are nothing but the energy level of an electron. So these energy level, if they are very far away from each other, we can assume that there is no interaction between these outer orbitals or outer energy levels. But as I bring them closer to each other, the first energy levels to interact would be the outer energy levels, correct? So as I bring them closer, the outer energy level will be the first to interact, and when they interact, like if there are many sodium atoms brought together with towards each other, they will start to again these are energy levels, and they will start to interact with each other, and some orbitals, the orbital of some of the atoms will gain energy, while some, because energy is always conserved, if some orbitals because of that interaction gains energy, the other orbital to conserve energy must have a lower energy. So the energy level of the outer orbitals get redistributed. Some will gain more energy, some will gain energy, and some will lose energy because of that interaction. So what basically will effectively happen is this energy band, okay, of the 3s. Now the standard level is this: because some have gained more energy, they will have more energy. So the energy level will increase, but because some have gained energy, in order to compensate for that gain energy, some will lose energy. So that energy level of those atoms, orbitals of those atoms, the energy of those orbitals will decrease. So in effect, what will happen is this overall energy band, because of that interaction, will expand, or the width will become more, because some are gaining energy and some are losing energy. So what effectively happens in a conductor is this energy band will increase. Okay, so let me draw it in a different color. So the new energy band will be something, when I bring many sodium atoms together, will be like this. Okay, so this we discussed about sodium, that when I bring lot of sodium atoms together, the outer energy band will increase. But this excuse me, this happens to all atoms, whether it is iron, whether it is silicon, whether it is carbon. The moment for all of them, the electrons are distributed according to Pauli's exclusion principle, and the first thing which happens to all is that electrons gets distributed according to Pauli's exclusion principle. And the second thing which is common to all the atoms when they are brought or stacked up together is their outer orbitals begin to interact with each other, and because when they interact with each other, their energy levels, they can some orbitals gain energy, some orbitals lose energy, and therefore the overall energy band increases. So this is common to all. Now what is not common is what we will discuss now, and it is based on conductor, insulators and semiconductors. So in conductors what happens is, so now we have here an example of sodium. Okay, now let us define what is valence band and what is conduction band. Valence band and conduction band. Okay, so valence band is the last band which has its whole orbital filled up, okay, with electrons to its maximum capacity. So valence band is the last energy band where energy band which is fully occupied, by electrons, to its full capacity. Okay, so here, for example, here in the case of sodium, okay, the last orbital is 3s, okay, but 3s orbital or 3s energy level is not filled to its full capacity, it is only half filled. So this is not valence band. Let us come to 2p, one level below. This 2p is covered fully with electrons. That means it has electrons to its maximum capacity, which it is filled with electrons to its maximum capacity, which is 6. Therefore, according to our definition, that the last energy band which is occupied by the electrons to its full capacity is known as valence band. Okay, so this is the valence band for sodium. Okay, where 2p is the valence band for sodium, because 2p is the last energy band which is filled with electrons to its maximum capacity. And what is conduction band? Conduction band is the band just above the valence band, which is not completely filled. Because it is not completely filled, electrons can move into this band. Therefore this band can be used for conducting, for the motion of electron. So suppose I have an electron outside, this electron can move, so this band can help to move this electron through it. Okay, because it is not completely occupied, it has space to accommodate the traveling of these electrons. That's why it is known as conduction band. Okay, so here we have sodium, all the lower electrons are fully filled. Okay, now what happens in conductor is, after the conduction band, okay, or after this 3s band has fully expanded, the outer orbital has fully expanded, it slightly overlaps with the valence band. Okay, so that's why this conduction, this last band which is the 3s band, because of the interaction with other atoms, it has expanded, and after the expansion it slightly overlaps with the 2p band. So 2p band is fully filled, okay, and 3s band is only half filled. Okay, so because it has overlapped, there is a very little energy difference between this and 2p and 3s. Okay, now we know that when we have collisions, okay, electrons, if they are at absolute zero temperature, then they are absolutely still. But we know at room temperature, or whenever there is a heat involved, all electrons are in random motion. Okay, so because they are in random motion, often at times electrons can collide with each other. Okay, because they are at random motion, electrons can collide with each other. And from heat transfer theory, when there is a collision, now there is different amount of energy transfer when there are collision between electrons, when there is a collision, different amount of energy transfer is there depending on the angle in which they have impacted and all other things. But from heat transfer theory, the average amount of energy transfer, there are millions and millions of electrons which are colliding millions of times per minute or per second or whatever that value is. But so the average of the collision energy transfer during that collision is kT, where T is the absolute temperature and K is the Boltzmann constant. Okay, this is just for an extra information. But what I am trying to explain here is, now whenever if the electrons are at not absolute zero, they have some temperature, there is collision between the constant collision between the electrons, and during that constant collision of electrons, energy is transferred. So some of the electrons may gain energy and some of the electrons may lose energy during those collisions. Now for the case of conductors, these electrons, this conduction band and valence band, they almost overlap each other. So there is very slight energy difference between the conduction band and the valence band. So because there is a very slight difference during these collisions, the electrons often from this band can go here to the valence band, to the conduction band, and vice versa. So there is a constant motion. Okay, so electrons can easily go into the conduction band here, and because they can easily go to the conduction band, they can easily conduct electricity. But in case of insulators, okay, what happens generally in case of insulator, if this is fully filled, the lower bands are fully filled, the valence bands are fully filled, okay, and the conduction band, there is even after those interaction and even after the expansion of the conduction band, there is large energy gap between the valence band and the conduction band. Okay, and because there is a large energy gap, this may be sometimes because the whole set, like this is 3p and this might be 3p or 4d, and this might be totally different. It might be 5s or 4s, sorry, the next level of orbital. So because of various reasons, the energy, the energy difference even after the expansion of the conduction band, because of the interactions with the atom, with the nearing atom, even after the expansion, the difference remains so high that these collisions are not enough to transfer such an amount of energy so that an electron jumps from this band to this band. Okay. And what about semiconductors? So obviously semiconductors, they do not overlap like the conductors, like conductors, but the energy gap is low enough. Okay, the energy gap is low enough that during collisions of electrons, at least some of the electrons are able to get, not all electrons may be able, like sometimes the collision will be in angles so that the energy transfer is not full. Okay, but at least from a statistical point of view, millions and millions of electrons are colliding with each other constantly. But out of that million collision, at least a few thousand or few thousands collisions are such that the energy transfer is big enough so that the electrons can be transferred. Electrons get so much energy, some of the electrons get so much energy after collision that they can go to the conduction band from the valence band, and then they can help in conducting those electric current. So this is a basic overview of why some conductors, some materials behave as conductor, some material behave as insulators, and some materials behave as semiconductors. Now, because our topic for today's discussion is semiconductors, let us quickly go to some more details about semiconductors. So semiconductors, here I am showing a typical structure of a typical semiconductor of silicon. Okay, so all these are silicon atoms. Okay, and if we study the structure of silicon, it will somewhat look like this. Okay, so if we study the structure of silicon, it will somewhat look like this, where each silicon atom is connected to 4 other silicon atoms. Okay, so now what happens is, so we know that the outer orbital of silicon has 4 electrons. Okay, so each silicon atoms share all these 4 electrons with its neighboring silicon atom, and that's why each silicon atom has 4 silicon atoms attached to it. Okay, now consider what happens if suppose this is the outer electron of a silicon and this is an outer electron of silicon, and these are all valence band because all orbitals are filled, and I know that this is a semiconductor where the difference in energy level between conduction band and the valence band is very less. So suppose this valence electron of silicon gains some energy and it moves to the conduction band. Okay, what happens? So then what will happen? Then this bond will be broken. Correct? So what I have is one electron going to the conduction band. Okay, so now this will help to conduct electricity. This conduction band, this electron will help to conduct electricity when it goes to a conduction band. There is another phenomenon going on here which will further add to this electron. What is that? Now what is that is, now this bond is broken. Okay, correct, and this electron has very similar energy to this electron because all are symmetric. Correct, all are the same type of electrons. So this electron has similar to this energy to this electron, which has similar energy to this electron, which has similar to energy with this electron, which have very same energy as this electron. Okay, so now all are at same energy levels. So because they are at same energy levels, they can easily change positions. So now I have an empty position here because one of the electrons has gone to a conduction band. So what will happen is another electron can easily take its place. For example, this bond, this electron, now this silicon atom is also connected to 4 other silicon atoms. So this electron can easily take the place of this, okay, and go into its position. So we have another type of electron moving now. Okay, so apart from this electron which have gone into conduction band, this electron is also helping to conduct electricity. But apart from this electron, further help is provided by this electron, which can now, because there is an empty position at the same energy level, this electron can now move to this position. Okay, and now when this electron moves into this position, there is an empty place here. Okay, so an electron from another neighboring atom can come and take this position. So in this way, this can also help to us to conduct electricity. So now I know the concept of this two ways in which an electron or a semiconductor can conduct electricity. Let me define two terms. Definition is very simple. First definition is holes, okay, holes or plus E. Okay, so now because I have a, when this electron went from the original electron which was here, went from valence bond to a conduction bond, there was an empty bond here, correct? This space became empty. So this empty space or empty electron is called hole or plus E charge, because an electron has gone, so net positive charge is here. You can imagine it like that. So this vacancy which was created because of a transfer of electron from valence band to conduction band, that vacancy is known as holes. Okay, so it is denoted by H. Okay, so or plus E or P, positive. Okay, it is defined as H or plus E or P. Okay, so this is one definition. Another definition is intrinsic semiconductor. So what is an intrinsic semiconductor? So this is a pure semiconductor, correct? Silicon, all are silicon, and if I put silicon together, they intrinsically behave as a semiconductor. Their inherent property. I did not put any impurity or any external material here to make them semiconductor. It behaves as a semiconductor naturally, so it is known as a intrinsic semiconductor. So in coming video we will see how an intrinsic semiconductor, can be the conductivity of an intrinsic semiconductor can be further increased. It can be made an even better conductor by introducing some impurities. Okay, so how it can be made even better by introducing some impurities, we will discuss that in the next video. Okay, thanks for watching.